Alright, how did we go with evaluating these guys? What did we get?
When did we do that?
Did I just ask you to do them?
Oh! I thought that was... No.
What did you get? 4?
Yeah, then 24.
24.
100.
What else we got?
124.
124?
Yep.
Yeah.
Where's my...
And 624.
624. You want to keep going? Mitch, can you do the rest? Right, 3,124.
Yeah. Because it's minus
Okay.
1.
Oh, okay, that was already subtracting 1. Okay. 3,124 and 5 to 6 minus 1?
15,620.
15,624. Okay. So in a similar idea, right, when we're looking at induction, we're looking at proving things, right? Do you remember what analogy I used? Dominoes, right? Yeah, I used dominoes. Like, we want to try prove one thing, and then we want to see if that condition is met for all the other things. Can you see a pattern that's emerging?
They all end in 4.
They all end in 4. So if they all end in 4, they're all going to be divisible by...
4.
They're all going to be even numbers. Can we check that they're divisible by 4? Let me check that these numbers here. So they're obviously all even, right? That's not a particularly interesting result. Let's see if they're all divisible by 4 though.
Yes.
They are? You checked all of
One
them?
is.
Okay.
Looks like it.
Looks like it?
Yeah.
Did you do up to the last one, Emma? You did?
Yes.
So are you convinced now that this is true for all values, for all powers of 5? Are you convinced that this will be true?
Yeah.
Yeah? So you don't think it's possible that, 5 to the 100, 5 to the 175, any of these powers, do you think it's possible that there might be one of them where they're not divisible by 4? Are you completely convinced by this?
5 to the 100 minus 1 is divisible by 4.
Is that enough to convince you?
Well, it does equal 1.9721526 times 10 to the power of 65.
Remember...
Well, it convinces me just like logically, if you do 5 to the power of anything, it's going to end in a 5.
Okay.
And then if you minus 1, it's going to end in a 4.
So like 14 is divisible by 4, isn't it? Because if it ends in a 4, so it's divisible by 4.
You got you there.
Okay, here's what I want you to get in the habit of thinking, right? When we're looking at these problems, it's not enough to just take a small sample and think, okay, there's some trend here, and we can continue that trend, right? I mean, it seems like there's some logic behind it, right? We can see some patterns, right? You are taking powers of 5 and subtracting 1, so perhaps that might be a reason to why they're all divisible by 4, but we can't know it until we can prove it, right? Conclusively.
Here we go.
And what was that proof? What was that methodology that I introduced last lesson, Mitch?
Induction.
Induction, right? Because induction is like looking at that domino effect. If I can look at it for one case, and I can prove it true for all the cases after that, then that's all the hard work done for me. I don't have to list all the individual
What would
cases.
it look like?
Well, what are you
5
thinking?
n minus 1 equals.
Good, right. So I want to prove that, exactly over here, 5 to the power n minus 1 is divisible. Write this down for me.
Is divisible by 4.
Yeah. Now I'm going to add a condition. These numbers here, they're all positive and they're all integers. They're all whole numbers. Right. So I'm going to say for integers n greater than or equal to 1. Okay. That's my condition. And I'm actually, for all these types of induction questions, there are a whole variety of induction questions they can ask you. Of all of them, we want to take those same steps. We want to find out that it's true for at least some value of n that I can find. Then I'm going to assume it's true or use a value where it is true. And we let that be n equals to k.
That wasn't the first step.
Yep.
Let's make it 1.
Right, yeah. I'm going to show you on the board in a second. I just wanted to get an overview of what we're about to do. And then the last step was I want to prove true for n equals to k plus 1. Because if I can find it where it's true for some value n equals to k, and I can prove it's true for n equals to k plus 1, the result that happens afterwards, that's all the hard work done for me. Right? I don't have to try and list all these individual cases. Right? I can scale this in a really broad sense. So, like you said, Mitch, the first step was...
Let n equal 1.
Yeah. Specifically, we want to prove true.
Prove true for n equals
Good,
1.
yeah.
Nothing is that too.
Okay, so what do I get? I just get 5 to the power 1 minus 1, which equals to 4, and that is clearly divisible by 4. So therefore, true for n equals to 1. Okay. And that's always going to be the easiest thing you got to do in an induction question. You're just testing that it's true for some value, right? The next step, right? Now you can write this in a variety of different ways. One of the quick ways is to just say assume true
K plus 1.
for, don't jump the gun yet, because I want to assume true for some n. Right? I know it definitely works for n equals to 1.
Yeah.
I want to assume true for some n where it actually works.
So
Okay?
just set n equals to K.
Good, yeah, that's what I want to do. And it's important that when I'm writing that, I actually write down what I mean. I'm assuming that 5 to the k minus 1 will equal to, now this is going to be slightly different to the sums we were looking at. I want this result to be divisible by 4. How could I write that as a general statement?
Something over 4.
Something over 4, yeah,
Maybe.
potentially. Or you think about how you get these numbers, right? This number here would just be 4 times 1. What would this be? This would be 4 times 6. This would be 4 times 30.
1, 2, 4 divided by 4. I'm on the case 31.
31, yeah, okay. So I can actually express, right? I can express this statement. If I want this result to be divisible by 4, I could say that is equal to 4 m. Yeah, 5 times an integer. And I'm going to use the letter m here. I'm just going to make a note where m is an integer. Where m is an integer. Okay, where m is an integer. Cool. And then this is where the third step comes in, Armand. What was it again?
True for K plus 1.
Good. True for n equals to k plus 1. And again, it's important that you write down what that actually means, right? It's important that you show that you understand what that should mean mathematically as a statement. And it's really saying you're replacing n up there with k plus 1. So I've got 5 to the k plus 1 minus 1 equals 2. And again, I want to have a result that's divisible by 4. And I could write the same process. I'm going to use a different letter though. Okay, I'm not going to use m. I'm going to use a different letter because essentially these two are different statements. Okay. For n, where n is an integer. Okay, now before I start, I should have done something earlier. What I'm going to do is I'm just going to rearrange this equation up here, okay? So where can I fit this in? Let's squeeze in here. Let's say I got 5 to the k. I'm just going to leave 5 to the k on the left-hand side. I'm just going to bring that negative 1 over. 4m minus 1, okay? Just going to rearrange them like that.
Is it plus?
Sorry, yeah. Cool. All right. So remember, when we are looking at proving it, what side should I start with?
Left hand side.
Good. Let's start with the left-hand side. So I've got LHS equals to just what I've got over here, 5 to the k plus 1 minus 1. Now, it looks like it would be quite difficult to go from this to something like this. But you remember, what did you do in the previous induction questions? You used what you found in step 2, and you tried to substitute it in to your statement in step 3. And so I want to look at what I have over here and see how I can get one of these things.
Can you say that?
What are you thinking, Amma?
You can. You can like for example, if you have
Yep.
5k minus 1 equals 4n, you can say that
This
if
one,
you,
yeah.
if you find 5k minus 1,
Mhm.
you can replace that with 4n.
Yeah, good. I could do that. Or, remember when I rearranged it over here, I could also say if I can find 5 to the k,
Yeah.
I could replace that with what? 4m plus 1. Good, right. So I go to this and I say, is there any way I could get 5 to the k minus 1 or 5 to the k? And it's a bit tricky to get 5 to the k minus 1 because we've got a power here. But I can actually express this power slightly differently.
5 times 5 to the k.
Okay, right, because 5 to the k plus 1 could just be rewritten as 5 to the k multiplied by 5 to the 1, right, using your different index notation or index laws, minus 1. And then you notice, hang on, I've got 5 to the power k here, but I also have 5 to the k
So
up here.
you put in 4m plus 1.
Alright, so let's go back up here now. So I'm running right to left, but so equals to 5 to the k times 5 to the 1 minus 1. And so instead of 5 to the k, I can just substitute what I had over there, 4m plus 1 multiplied by 5 to the 1 minus 1. And just say where you got that from, right? We got that from step 2. Now let's expand this out a bit more. So I've got these brackets here. I've got 5 multiplied by 4m. So that's just 20m. And I've got 5 multiplied by 1. That's 5 minus 1. So what have I got now? I've got something that's simplifying out quite nicely. I've got 20m plus 4. What do you think my next step would be? Because remember, don't forget about what the goal of this whole statement is. I want to show that for n equals to k plus 1, that result is divisible by 4. I want to get 4 multiplied by something where that something is an integer. So I come back to here. What do you think I want to head to next? What do you notice about these two numbers? Or these two terms?
They're both divisible by 4.
Yeah, they are, right. So if they're both divisible by 4, what's in common? It's just 4.
Yeah.
Right, so I could factorize, right on. If I factorize it out, I get 5m plus 4. Okay, and that's pretty much what we got over here, right? Now I can take one extra step and say that's equal to 4n. And the reason why that's equal to 4n is because 5m plus 4 is an integer. All right, if you think about where we got 5, what m was before, right? M is just some integer that you're using. And if you're just doing operations on an integer, only using integers, you're going to get an integer as a result. So it makes sense that this can be replaced by n, which is what you were trying to prove. And then remember your favorite part, Mitch, the conclusion? How am I going to conclude?
Therefore maths.
Hence,
Hence maths.
hence, if the result
What I write before.
is true for n equals to k, there's a few variations you can do.
I wrote consonants.
Then it is true.
I got it.
So sit tight. For n equals to k plus 1, it's true for n equals to k plus 1. And therefore, the result is true by mathematical induction. How awesome is that? We proved that, not just from observation, but through the induction method, that statement is actually true for all positive integers n.